Right, hello. This is one of the few English talks today. So my topic will be tracing embedded systems for holistic debugging. So I kept the title a little bit abstract on purpose. Reason for that is today's agenda is a little bit broad. It covers a lot of topics more from a high-level view and is mostly applicable to embedded systems, but you can also apply this to other Linux-based systems or even systems that are not even Linux-based. So today's agenda will be what makes embedded systems especially hard to debug compared to, for example, desktop systems and desktop software, showing some traditional debugging methods, shortcoming of said traditional debugging methods, a quick introduction to eBPF, and what I call tracing-assisted debugging using uprobes. Lastly, I will also cover exporting the traces from the tracing-assisted debugging using the OpenTelemetry project, and where does this actually make use, where does it make sense to actually use this, and a wrap-up at the end. So why are embedded systems harder to debug? First of all, most of the time they are very resource constrained. So for example, we already had OpenBMC named here today a few times. Most of the time it's booting from a SPI flash that only has a few megabytes to boot from, like 32 or 64. We don't have a lot of RAM to start up hefty debuggers, and also CPU resources are also usually rather constrained. Maybe you have 1 core, 2 cores, very rare cases for. So there's not that much compute that you have available. They are usually, for that case, prone to timing or resource starvation issues. So if you run the same software, for example, in a virtual machine, you're not seeing any of these issues because your system runs a lot faster, and therefore some of the problems are just not visible. And for embedded systems, you mostly have no direct user access. You have no screen attached, you have no keyboard. Maybe there is somewhere in a remote location, in an industrial plant, in a data center, on top of a mountain, who knows where. And most of them obviously don't have an IDE on top that you can just work on. Therefore, your built-in debugging tools, for example, if you have VS Code and put some breakpoints here and there and then just start your code in debugging mode, that's something that doesn't work with a lot of helper steps included. And all of these tools have overhead on the system, and creating overhead will change the behavior of embedded systems, and this is something which makes debugging even harder. And also deploying a debug build on these systems, especially if you do something like printf style debugging, takes a lot of time, and maybe the issue then doesn't even occur. So here's some traditional C, C++ debugging methods. I just list a few here for your overview. For example, you build a binary with some debug infos, dwarf tables, full symbol information, but this is something that we can't do on embedded systems because binaries get so large that they just won't fit on a flash storage, for example. You would use something like GDB or LLDB if you prefer LLVM-based tools. Those are good for debugging C, C++-based binaries. There is also a talk following my talk right after that covers this in much more detail than I will today. And something that you use on remote systems usually is something called the GDB server client mode, where you have your GDB server, which is a stripped-down version on the remote machine, and then a GDB client on your actual machine that is debugging the embedded system. Or obviously, the classic printf debugging method. I'll cover it here because, to be honest, I think everyone here used it at least once. Put a print before a faulty function or after a function and see what's being output. Or halting a system to look at breakpoints, look at memory, something you can do with GDB, or post-mortem analysis where you get a core dump which shows you what the storage looked like the moment a tool crashed, and then you can analyze it on your system offline. But what are the shortcomings of these methods? They all sound like they work for the most part, and that is true, but usually you only target something very specifically, a single binary. Debugging a whole system, especially where multiple services, multiple cores, and sometimes even multiple embedded systems are involved, is something that is really hard to do using these tools. It is also slightly harder to set up the GDB client-server model and GDB in general, hence there's a full talk following mine that just covers this topic alone. And doing iterations with printf debugging, because you can't really find the faulty point on the first try most of the time, takes a lot of time, especially on embedded systems where the whole deployment and update steps are just much more tedious than pressing compile on your machine and just rerunning a tool. And also altering binaries, as I said, could sometimes even hide bugs. Maybe a different memory location now makes a bug disappear completely. Or just adding more prints makes a bug disappear because now you spend more time printing and therefore another service suddenly can execute that it wasn't able to do before. We name these usually Heisenbugs. Some other shortcomings are very subtle issues that you don't notice right away. For example, core dumps only occur when a system crashes, but maybe your system doesn't crash. Maybe you just see weird latency spikes every now and then, or some other odd behavior like spamming, IRQ storms, something that isn't really showing up while you're debugging it, but every now and then it is, and it's causing a lot of troubles in the field. Also, race conditions are something that is harder to find, and as I said, debugging just multiple systems, for example, if only one of them functions fine alone, but suddenly you have 10 of them running and one of them misbehaves only when it is connected to the cluster of the rest, is something that is really hard to debug. And therefore, I don't call these holistic by looking at a system as a whole, but rather a targeted approach. So now, how do we actually solve this? One way to do this is eBPF. So I'm giving only a short introduction to eBPF. We had a lot of great eBPF talks in COSCUP this year. If you visited some of these, you might already know what it is. It stands for the Extended Berkeley Packet Filter, and it is much more than a packet filter, but it just originates from that. You can think of it more like a in-kernel virtual machine kind of progress. So it has its own assembly architecture, so it's not x86, it's not ARM, it's not RISC-V, eBPF is its own format. And you can compile these eBPF programs anywhere and then also have them run on, for example, an ARM machine or an x86 machine or a RISC-V machine without a lot of modification to them. They have something called BTF, which is the type information which tells the BPF program what it's capable of doing on the target machine. So why do we want to use eBPF in the first place? Tools written in eBPF are really, really small. As I said, like on embedded systems, we don't have that much spare space left. And eBPF programs are only a few kilobytes, maybe maximum a few hundred kilobytes in size, which is totally fine, at least on most machines. They are loaded into the kernel directly, and they have a negligible overhead. So executing them causes almost no disturbance in the user space. There is a slight disturbance, but it's so low that you usually can't measure it unless your eBPF tool is doing very, very extensive analysis. And the most important part, they do not require any modification whatsoever to the user space. So you can just run the same release binaries that might cause problems in the field, and it will just work the same way. And by now, eBPF is widely available, so anything that's using a rather recent kernel can use it. I don't actually remember which version they got added, but they've been there for quite some time. So here's an overview. How does eBPF actually work? So you usually have something in the user space that interacts with eBPF. I'll show two examples, one where we just use the command line and the sysfs to instruct the kernel to use it, and one where we compile a dedicated debugging collection program that will do it. It will push the bytecode during runtime or during boot up of the system to be debugged into the kernel. It runs through a verifier so that you're making sure that your debugging program is not causing more issues than you want to solve in the first place. And from there, the BPF virtual machine in the kernel has a lot of endpoints like kprobes, uprobes, trace points. You can only also do performance event measurements, all kinds of things. And to get the information out of the Linux kernel back into user space and therefore back to you to actually analyze on your system, they have something called maps. These maps have asynchronous reads, usually via ring buffers or other measures that can be then transported back to the user space and be analyzed by you from there. So what we will focus only on today are uprobes and kprobes, and uprobes more specifically. So kprobes stand for kernel probes, and they trigger on kernel internal functions that you define, something like syscalls, for example, or I/O intensive operations where you want to know when I/O is being used, how it's being used inside the kernel directly. And uprobes do the same, but for user space. You can hook them to any user space program or library that you have on your system. The only constraint is needs to be an ELF library, which, if you're running a Linux system, is about every binary. And can be freely chosen by the user what you actually want to test. So you don't have to test the whole system. You can only test a subset of programs or libraries that you consider faulty and therefore want to analyze. And they also do not interfere with the normal execution of the system. So the user space program, unless it's been rigorously designed to detect this, has no idea that the kernel is introspecting it, and it runs just as normal. So here we have an overview of how this could look like usually by using, for example, here an example application. And this example application is doing calls to a gRPC library, for example, grpc.so in this example, where it's the C implementation of gRPC to do some calls. And this library is something that we can look at with uprobes. For example, if there's a certain function in there that we want to analyze, we can tell it to hook to this library and the function name. I'll go over that in more detail on the next slides. And that, for example, can do something like talk to the network interfaces in the Linux kernel, where we want to send, receive, close a socket, something like that. And maybe the networking in the Linux kernel is faulty because sometimes it's not your user space program, but you got an older version of a vendor-supplied kernel or a kernel with some out-of-tree modules that might cause issues. And this is where kprobes can come in. And you then configure your eBPF program to listen on some certain kernel functions. So how can those actually help us debug more specifically? So it allows us to observe any function entry and exit of a library or a program that we have on our embedded system. And for example, we can use this to uncover patterns of data propagation where maybe in one function incorrect data was generated, and then in another function it was simply passed in, but we had a missing error check, and then the whole system blows up and we just suspected that function B was faulty, but in reality it was function A that generated the wrong data in the first place. And by just hooking our analyzer to multiple functions, maybe even in multiple binaries and multiple libraries, we can now look at all function invocations throughout the whole system, how they are being entered, with which parameters they have been entered, and when they have been exited. And also we have very fine-grained timestamps, usually to the nanosecond, where we can also see that if one function spends an abnormally large amount in execution, which we never expected to happen and causes weird timeouts, we don't have to guess now what problem inside a binary is actually causing our slowdowns, and don't need to increase timeouts limitless here, because we have some systems, for example, where we just increase dbus timeouts to absurdly high amounts simply because there's one function in one tool that's misbehaving, and with this you can actually see latencies of individual functions and see where time is being spent. And this is helpful to narrow down where we can actually now hook on with traditional debugging methods. So it's not our universal solution to find the bugs, But this gives us a good pointer to where now use GDB and something else, because now you don't need to guess which tool and which function do I need to look, which takes oftentimes a lot of time. Now you know where to look. Now you know which function has a problem, and now you can whip out GDB and introspect this further. So here's an example on doing this in Go code. I also have another example that's not using Go code. It's just very short code snippet with a main function and a greeting function that simply just takes in a string and prints it out. I have to use no inline here because, as I said earlier, this whole principle works on ELF binaries, and the Go compiler would optimize this out. If we did not have this information in the ELF binary, then our uprobes wouldn't work, because now it's not a dedicated function that we enter, it's part of main. And debugging main is something that's really hard to do. Therefore, you need to make sure that if there's a function, it is still an individual function inside the binary. And yeah, I'm using nm there to look at it and can confirm we have a function called greet. So what do we do with this now? First, we write a very short snippet of C code, which is our eBPF program, which is only this small amount down there. So we tell it, for example, in C up there, that we have a greet event, and this has a parameter in this case that we're taking, which is the string we're feeding into it, and some other more details that I'm not going too deep into today, but you can look those up, which tells us what this map contains, how large it should be. This is a ring buffer that we can throw back to user space. And in here, we're just, first of all, reserving the ring buffers so that we have some space from the kernel back to the user space to provide this information. And then we can use Clang there to compile this tool. We're telling it that our target is not ARM, not x86, it's BPF. And then it will compile a .o file that we can later on use. So there is a demonstration now here where we run this Go binary where it randomly selects it, and next to it is actually our debugger running that sees all the function invocations that are happening. It can trace them with a timestamp. It sees how many input parameters it has seen over time, how often it has seen them over time, and prints them out for us so that we can look in one process what the other process is doing. And we can also export this information over the network, so we don't have to do this on the embedded target itself. That's just one way to just make it easy for the demo. And now an example that doesn't use any code whatsoever, but just a command line if you want to quickly prototype something and don't want to write a whole program. As I said, the sysfs is also exporting a lot of good endpoints for us to use here. There are three ways to actually set up these probes and work with them. So the parameters look slightly confusing, but we have a return probe and a normal URED probe where we do the return is basically the function exit on which we want to do something. The general uprobe can be used for anything else. And we have a way to just clear the probe. So in this case, what I want to do is I want to instrument the bash binary. It's a completely unmodified shell binary on the system. And first of all, the call that I want to instrument inside bash is the readline function, which is the main function inside bash to actually read the input and then work with it internally. So first, I open GDB on bash just to find out where is readline inside my binary. So here I just open it, find out where's readline, and it outputs me the address where this will be. And then we set up a probe, we name it bash readline. We set it up on bin bash at the location where our function is, and place this into syskernel tracing uprobe events so that now we have set up a new probe, and we gen echo 1 to enable it. And then in parallel, I typed in some commands in a different window on the same system. For example, I put in cat trace pipe, ls, who am I, and so on. And all of these events I can then look up at kernel trace pipe From there, I can see all of the events that I previously set up a uprobe for, and can see, for example, if there's some input that looks really weird, something like 0xFFFFF, where something was not a string, but someone tried to put in hex that was wrongly escaped, something like that. And this is something that we can do on any binary, even with strip debug information. We just need to know the function's name, or in case if we do it via the command line, we need to know the memory location. So here's the same, not via the memory location, but writing a eBPF program in C again that we load into the kernel. The same example, we look at bash and we want to this time know the readline function. Here we don't need to know the memory, but we just tell it I want to look at readline. This is something that happens there in the sec part at the very top of the C function call. We have a we create our probe there, and in that case, we just print out the process ID that is actually doing something with bash, and also print out again what actually happened. For example, in this case, if someone outputted a string using bash, we will see it in our debugger now. But all of this is still a bit clumsy because you have a lot of console output, and collecting console output is something that is, especially on some embedded devices that might not even have a console, something you can't do. So we want to aggregate all of these informations that we got from K-probes or U-probes on our system. And the best way to do that is in a standardized way that you can use a bunch of tools on the market right now that are also all open source, including the protocol itself, which is the Open Telemetry Protocol, or short OTLP. These traces can be emitted via the network and then, for example, collected on your machine or on a debugging server elsewhere that is collecting these traces. And this is something that helps you identify your whole fleet. For example, you can have these probes active at all time. Be mindful, because if you, for example, trace every function of every binary, this will still create a bunch of network traffic. So be mindful of what you actually want to debug here, or if there's something you want to trace. And if you have good monitoring in place, you can see issues arising inside code that has been deployed a lot sooner, so you don't need to wait until a device completely crashes or is being sent out by a customer again. Because now you can see in your monitoring that this device is misbehaving, and we can now see that more devices start misbehaving and an error starts propagating throughout multiple embedded machines. As a small side note, we actually used a similar approach on one of our embedded BMC systems, where we monitored, for example, a weird issue of disk performance being abnormally slow. And we then looked at all the traces that we created and saw that the disk usage always went super bad when the fans ramped up at the same time by comparing the timestamps. And what actually happened is that because the fans were causing so much vibration in the chassis, the actual read heads of the drive started vibrating, and we had a lot of I/O errors. And this is something that you can't really debug easily, because you're wondering, like, how does a fan have to do with I/O disk space being suddenly worse? But tracing helped us uncover this by just having two completely unrelated parts of a system debugged and having them show up, for example, in something like this. Here you can see one of these traces visualized. You see how much time is being spent for each function, at which timestamp. You can see bottlenecks easily. You can see misbehaving functions that take a lot longer than all the other functions. Maybe optimize them out, see if you want to give them more or less CPU or memory resources to prevent other future bugs. And where does this really make sense to use? Because it sounds wonderful, but it is not the golden solution, as I said. So any system that is really hard to get to and really resource constrained, because there are better debugging solutions if you, for example, are debugging a front-end desktop application, something like that. You don't really need this, because using your IDE or debuggers that will be showcased in the next talk are a lot better solution there. It's really good to solve complex bugs like this fan disk I/O degradation problem, for example, it helps for initial error spotting in the field that only show up every now and then, but proactively already work on some bug fixes before they show up on the customer side, and helps you to further narrow down functions or libraries that cause problems in the field. So an example that I want to give here quickly is OpenBMC, for example, uses dbus, and there are a lot of services interacting with each other. And maybe one of them is propagating a wrong value via dbus, but you don't immediately know that it is wrong because it could just be a string that's not null terminated, something small like this. And then a different service is just crashing. And now you're wondering why your different service is crashing. But this whole thing could have been avoided if you, for example, started monitoring other services altogether and already saw that this function is emitting something that just doesn't look right. And if you then figured this out, you can start calling GDB, as we will see in the next talk, and then actually find the real bug inside the code and not only narrow it down to the function that might be problematic. So yeah, without any modification, this usually works as intended. I have some smaller, like further reading. Those are not really important. You can also instrument code where you can save all the eBPF code altogether. You don't need it anymore because now your code can emit these traces very fine-grained. You can set up tracers yourself inside functions. This is something that requires code modification and a lot of planning up front. So therefore, I will not go into detail here. As it's not a black box debugging solution, it requires a lot of modifications. Another framework that is worth noting is LTTNG. It's a out-of-tree Linux kernel tracing toolkit. As I said, like it's out of tree, but it still supports the same kprobes and uprobes because those are kernel internal structures. It's a bit more complicated to set up, but it does not rely on eBPF. For example, if you have a system that doesn't have eBPF, this might be an alternative. And it's slightly less convenient to convert the traces to OpenTelemetry. So now, to wrap the talk up here for today, embedded systems are inherently harder to debug, but there are solutions to ease debugging. The eBPF in kernel VM allows you to debug user space and kernel space using uprobes and kprobes. OTLP is a widely supported format in the industry to aggregate, visualize, and analyze these traces and put them in context. And tracing-assisted debugging can be used to find bugs that traditional methods can help to actually bisect bugs. Or how I like to say to that is, tracing is the large fishnet to catch them all, but not one specifically, while GDB is the actual spear to find the fish that is really the problem in the bunch. And they always work best together, having tracing-assisted debug to figure out the rough direction that you need to go, and then GDB to actually find the really bug. And that's about it. Thank you very much for listening. According to my timer, I have 1 minute. Yes.
Thank you for your introduction. A quick question that I'm curious about. How do you know that fan shaking is related to the problem of the system is on slow heavy?
Yeah, on these systems we had a bunch of traces, and by simply just having a lot of graphs like next to each other, we could see a spike in fan increase, like because we visualized a lot of these events, like not just one event in particular, but we created hundreds of them. And we saw that really just by looking at the screen and creating graphs of the events that whenever the fans ramped up to 100%, we could see the disk I/O decreasing. It's like always at the same spot in time because the traces had timestamps, and on a few hundred machines, the same symptom happened where when the fans ramped up, the disk decreased. And we figured then one has to do with the other. So we went and took one of these systems out of the rack and just removed the fans and see what happens now. And by just removing the fans, the disks never decreased in performance. So we had to figure out that something with the fans causes the problems. And it was really just by chance that someone said like maybe it's vibration. And we then just removed the fans, really just physically vibrated the machine, and we could see the same decline in I/O performance. So yeah, that's just one example where this helped narrow down a bug. And we just fixed it by tweaking the function that was doing fan control to have a lower threshold to create less vibration and therefore better disk I/O.
All right, thanks, Marvin.